In Chapter 2, we're going to look at the derivative. And we're going to start slowly by first talking about speed and velocity and talking about how to measure speed and velocity. So in this section, we're going to learn how to calculate average velocity, and we're going to interpret instantaneous velocity as a slope on a graph. We're going to compute instantaneous velocity as a limit of average velocities, estimate the slope of a curve, whatever that means, and we're going to calculate limits of different quotients as h goes to 0 algebraically. So first we're going to start talking about average velocity, and it's important to note what velocity and speed are and how are they different. So speed and velocity are interchangeable when we're talking about positive values. If your car is going 50 miles per hour, that is both its speed and velocity. However, velocity can be negative and speed can never be negative. So if you're going in reverse, you have a negative velocity but a positive speed. Speed is just the absolute value of velocity. For a lot of problems we do, when we're talking about positive velocities, we'll use speed and velocity interchangeably. All right, so first example, on a road trip, a car travels 300 miles in 4 hours. What was the average speed of the car during that trip? Well, we know that speed is going to be the distance traveled over time. In this case, that's going to be 300 miles over 4 hours. Which we get 75 miles per hour. And again, that is the average speed. So this does not mean that the car always traveled at 75 miles per hour, but it means that overall it went 75 miles per hour on average. All right, so in general, average velocity or average speed, if we're talking about only positive values, from two different times, t equals a to t equals b, is going to be the change in position over the change in time. If f is a function that represents the position at time t, we can think about f as distance traveled. Then we get that average velocity is f of b minus f of a over b minus a. And we'll see that this is very similar to some things we've seen before in algebra. This is the change in the y values, the function values, over the change in the x values. Maybe we've seen this as delta y over delta x, and this is the slope of the line through these points. So when we're talking about average velocity, in some way we are talking about the slope of some line. So now let's think about this with a graph. So the graph below is going to show the distance covered by a moving object. This is going to be our function of t. Plug in different units and we get different distances that we have traveled. And the question here says to estimate the average velocity on the interval t equals 1 to t equals 3. So we said that we're going to have 2 points here. The first one, if we look at t equals 1, we're going to look at the point here 1, 10, which is 1, f of 1. And the second point is the point at 3, 20. So average velocity here is going to be f of b minus f of a over b minus a. And note that we are calling this first point a f of a, and the second point b f of b. So this is going to be f of b, which is 20, minus f of a, which is 10, b, which is 3, and a, which is 1, gives us 10 over 2, or 5. And the units here should be miles per hour. That's because the numerator is measured in miles, the denominator is measured in hours. So, something that we didn't show on the graph yet, but we said that this is going to be a slope of some line, and the line that it's a slope of is the secant line that runs through those 2 points. And the secant line is just a line that joins 2 points on a function. See that at the bottom of the page here. The line joining a f of a and b f of b is just the secant line through those points on the graph of f of t. And we are defining the average velocity as the slope of that line. So now we really get into our first calculus topic of this chapter, and that is, what is instantaneous velocity? How can we tell the speed of an object at an exact moment in time? And really, that's kind of a question to talk about. How does a speedometer in a car work? So oftentimes we think about a car traveling in these problems with average velocity. And if I asked you, how can we tell the speed of an object at an exact moment in time? A good response might be that we could just look at the speedometer and it tells us that we are going exactly 53 miles per hour at this time. But how does the speedometer know how fast we are traveling? And that's just a good question to kind of ask. And I urge you to pause the video for a second and take a couple minutes if you've never thought about it before and try to think of a way that a car could tell that, or the speedometer could work. How does it know what the speed is at any time? So let's talk about this speedometer idea. The speedometer in a car is related to the tires in the car. So here is a tire on the car. All right. The car has a uniform size of the tires, a certain radius of those tires, and it knows that one full revolution of those tires is going to be the circumference of the tire. And that is going to be 2 pi r. So the car can track how much time it took to do one full revolution of a tire. And then with that, we can tell the distance traveled. So note that this is the distance traveled, the change in position, and then it tracks how long that's going to take, and that gives us the speed. So note that this is not instantaneous velocity. This is, however, the average velocity over a small time interval. So that being said, all of this is just an estimation for the instantaneous velocity. And the speedometer or the car really doesn't have any way to calculate the exact instantaneous velocity at any time. The best it can do is give an estimation, and it's a pretty good estimation because a tire goes around once in a pretty quick amount of time, and there's really no need to tell exactly how fast something's going at any specific time. Another maybe indication of this, another kind of way to think about it, is a radar gun for a cop that uses uh, laser beams to kind of think about how does it bounce off an object and how does it change to give a different kind of estimation for instantaneous velocity. And again, it's just if the estimation is good enough, then it might as well be the instantaneous velocity. So all of that being said, how can we tell the speed of an object at an exact moment in time? The whole point is that it's very difficult to find the exact speed at an exact moment in time, but we can estimate it by just making the time interval very, very short. That's the big idea. And then we're going to bring it all together and we're going to use a limit to actually give the exact instantaneous velocity. So we use average velocities over smaller and smaller time intervals to estimate the instantaneous velocity. And in practice, we never actually know exactly what the instantaneous velocity is. We can just say it's very close to this value. So now let's think about instantaneous velocity in a graph. So here's a graph of f of t. F of t is the position of some object at time t. And we want to find the instantaneous velocity at time t equals a. Well, we just said the best that we can do is look at the average velocity on an interval close to a. So we're going to have b be a number close to a, or a value close to a. And what we can do with that is we can look at the average velocity between those 2 points. We're looking for the slope of the secant line. Which we know is f of b minus f of a over b minus a. But what if we let b get even closer to a? Then we would get a different secant line with a different slope, and we can just continue doing that forever. So we're letting b get closer and closer to a, and then we're looking at the corresponding secant line and the slope of that line. And we can see that that line is getting closer and closer to some special line that we call the tangent line. So the secant line is approaching what we call the tangent line. All right, and this happens as B gets close to A. And note that we could have done this in the opposite direction as well. We could have said that B is less than A, and all of this works the exact same as well. And this is our idea of limit, that there are two ways that we could approach A, right, to estimate, in this case, the slope of the secant line. So the actual tangent line here is going to be very close to the line that I drew the last one. Right, so maybe this is the actual tangent line. of f of t at t equals a. And we think about the tangent line is, it's like a line that hits the function exactly at that one point, a, f of a. Right? All of these lines agree, they're all the same at this special point, a, f of a. And it's just the slope that's changing if I use a different value for b or if I'm using the exact tangent line. In this course, we're going to have to draw a lot of tangent lines. It's a very important part of calculus, and you'll get better at kind of seeing how to draw that tangent line. And it really is just kind of thinking about what is the slope of the function at that point. So now let's look at the definition of instantaneous velocity, bringing this all together. So we're going to say that instantaneous velocity at t equals a is the slope of the tangent line of the graph at the point a, f of a. That's what we showed on the last last thing. So if we have some kind of function here, and we're looking at a, the instantaneous velocity is this tangent line, and it's the slope of that line is the instantaneous velocity. Now the problem is that it's very difficult to just know exactly what is the slope of the tangent line. In fact, that's the entire point of chapter 2, is this idea of the derivative is going to be the slope of the tangent line. We can also think about instantaneous velocity as the limit of the average velocity between t equals a and t equals b as b approaches a. This is what we did in the previous page, that if you let b get closer and closer to a, and you look at the slope of those secant lines, then that gives you the instantaneous velocity. Putting that into math notation, we have this limit. The limit as b approaches a, f of b minus f of a over b minus a. So what this is talking about is we're letting b get closer and closer to a from both directions. And then the actual function here is just the slope of the secant line of those points. If we go back to the previous page, we let b get closer and closer to a in both directions, and we look at the corresponding slope of the secant lines to give us the slope of the tangent line. Now we're just using it as a limit. That's how we can say let b get closer and closer to a. This, however, is not the definition that we are going to use very often. We're going to use the one in the next line, and that involves the idea of what h is. So let's define h as the distance between a and b. So if we have some a here, instead of thinking about b, what we can do is think about a value a plus h. And that's really what we're calling the value b. And we're just letting that value get closer and closer to a, which is another way of just saying let h go to 0. Now, at first glance, this might seem like a more complicated way of doing the instantaneous velocity, but in practice, it's usually much easier to think about this h kind of thing here. The one that we box here, the f of b minus f of a over b minus a, in practice, algebraically, can get rather cumbersome. So we're going to use this h notation to represent the distance. And if we want b to get closer and closer to a, I want the distance to go to 0. So my 2 points here, a plus h is b. We have f of a, and then h is the distance between b minus a. So writing it again, this is what we're going to call our instantaneous velocity. The limit as h approaches 0 of f of a plus h minus f of a over h. We call the thing inside the limit, this is called the difference quotient. And you may have seen this in a pre-calc class. And if you did, you saw it because you're getting ready for a calculus kind of idea. So how can we remember what this is called? Difference quotient. Difference means subtraction. And we have a subtraction right there. And quotient means division. And we have a big division in this as well. So it is the subtraction division, the difference quotient. This is the first major idea in calculus. This idea of what is instantaneous velocity, how are secant lines involved, and how does it how does the limit give us the actual definition of instantaneous velocity? We're going to be going over this topic in a few more sections to lead up to the derivative and understand what the derivative is really talking about. And in the next video, we'll go over some practice problems to solidify some of these ideas.